Welcome to Marine Gurukul video series. We are happy to present our Great Circle Sailing video 2 in continuation to video 1 earlier. Now before you watch this video, kindly make yourself comfortable about the contents of the earlier video, that is Great Circle Sailing 1. This video shall be taking forward the learnings of the earlier video, especially in respect of correct drawing of the PAB triangle, marking of the parts of the PAB triangle from the information in the question, application of cosine formula to calculate the missing part, especially angles A and B. In case of any doubt, please re-watch the earlier video before proceeding with this one. We start our discussion by understanding as to what does vertex mean. Let us take any great circle on the surface of the earth. So we see in the diagram the sphere of the earth showing up. We have the poles of the earth coming up on the diagram, followed by equator, and now we take any great circle except the equator. So equator has been left out of our discussion currently. So we take any other great circle. You can see an orange great circle showing up in the diagram, and we consider randomly points on it marked from A to H. So you can see these points also randomly showing up on the great circle drawn on the surface of the earth. Now if a vessel moves along this great circle starting from A along the direction of the arrows which are coming up on the screen, so she goes right round this great circle and returns back to point A. What do we see as the vessel sails along this great circle? We see that at each point the vessel has a different course. Why? Because the great circle track cuts the meridian at each point at a different angle. Also, the coordinate of each point along the great circle, that is their latitude and longitude, are different. And what do we see as far as coordinates are concerned? That of all the points along the great circle, point D is the point where the vessel shall reach the highest northerly latitude, and likewise point H would be the point where the vessel shall reach the highest southerly latitude. These 2 points D and H, where the great circle has the highest latitude, or the points having the highest latitude along the great circle, are the points referred to as the vertices of the great circle. So D and H are the vertices of the great circle. So based on the explanation of the vertex of a GC is a point at which the GC reaches the highest or maximum latitude. In other words, these are the points on the great circle which are closest to the poles. Now, based on this discussion, let's evaluate as to where are the vertices of the meridian. We know all meridians run north-south. Their highest latitude are the geographical poles. Therefore, vertices of every meridian happen to be the North Pole and the South Pole. Where are the vertices of the equator? Now, if you recall, when we started our discussion on vertex, we had left out equator. Why? Because equator is a very special great circle which runs in the east-west direction, and latitude of every point along the equator is 0 degrees. So therefore, the concept of vertex shall not apply to equator. Why? Because the latitudes are measured with respect to equator itself. Now, having understood what vertex means, let us understand some of the features of the vertex which will help us in solving certain questions. Now, every great circle, of course excepting equator, has 2 vertices that are diametrically opposite to each other and one located in each of the hemispheres. With respect to this great circle in question here, we can see it has 2 vertices, vertex D and vertex H, diametrically opposite to each other, vertex D in the northern hemisphere and vertex H in the southern hemisphere. At the vertex, the great circle track is exactly east-west, and the other way of saying the same thing is that the great circle course of the ship at the vertices is east or west. That means it does not have any northerly or southerly component. Now, to understand this, let's have a look at the highlighter moving along this great circle track, and we can see as it is moving along the great circle track, the northerly latitude is increasing. And we all know that this increase in northerly latitude is because of a northerly component in the course. And of course, this northerly component is continuously changing. What do we see as the vessel goes past point D, that is the vertex? The vessel's northerly latitude starts decreasing. Now we also know that if the northerly latitude has started decreasing, the course must be now having a southerly component. Therefore, the vessel, as it was moving along here, the track here, had a northerly component of the course, then it has the southerly component. So somewhere this change has taken place, and the place or the point where the change takes place is point D, where the northerly component was continuously decreasing, becoming zero at the vertex before the southerly component sets in. So at the vertex, there is no northerly component of the course, there is no southerly component of the course. Therefore, the vessel's course will be either east or west. As the vessel is always aligned along the great circle, therefore, it also means that the great circle track at the vertex or the vertices is running in the east-west direction. The vertices will be located with a D long of 090 degrees from the positions where the great circle cuts the equator. Now, this great circle is cutting the equator at point P and point F. Vertices are D and H. That means D long between B and D is 90, D and F is 90, F and H is 90, H and B is 90. It's very simple to understand that. If a vessel starts from B, goes along the great circle track and comes back to point B, the D long is 360 degrees. Now these points, that is point B, D, F, H, B, they divide the great circle into 4 quadrants. And now since all these 4 parts are equal, being the quadrants of the great circle, so if along the entire great circle the D long was 360 degrees, then the D long for each quadrant shall be 1/4 of it, that is 90 degrees. The latitude of the vertices will be equal to the inclination between the plane of equator and the plane of the great circle, or the angle at which a great circle cuts the equator represents the latitude of the vertex. So first let us identify the angle between the planes of the equator and the great circle. This is the angle in our case, which is the angle of inclination between the plane of this great circle and the plane of equator. Now if we join this point D with the center of the earth with a straight line, I'm sure we can all visualize that this particular line shall be in the plane of the great circle. So if this line is going to be in the plane of this great circle, then this line shall make the same angle as this one with the plane of equator. And we all know that the angle subtended by a point on the surface of the earth with the plane of equator at the center of the earth represents its latitude. Therefore, this angle of inclination becomes the latitude of the vertex. The great circle track intersects the meridian of the vertex at 90 degrees angle. This issue has already been addressed when we inferred that the course of the vessel at the vertices would be east or west, or the great circle track shall be east or west at the vertices. And we know these directions are measured from true north, and north-south is represented by the meridian. Therefore, the angle between the meridian and the great circle at the vertices shall be 90 degrees. A vessel's track may or may not pass through the vertex of the great circle. Of course, the entire great circle has only two vertices. We may be traveling only over a part of the great circle track. So it may include the vertex or it may not include the vertex. For example, if I travel along this great circle from B to C, then over this arc, I do not include any of the vertices. But if the great circle, if I have to travel from C to E, then I shall be passing through vertex D. So my track may include a vertex or may not include a vertex. In our calculation, we shall be dealing with the vertex that is closer to our great circle track. So if it lies within the track, obviously that's the closest one. If it does not lie within the track, then our interest would be in the vertex that is closer to our track. To figure out whether the vertex of the great circle lies within the GC track of the vessel or it lies outside the GC track, we use angles A and B of the PAB triangle. We calculate the angles A and B, and if angle A and B are both acute, that is both are less than 90 degrees, then the vertex lies inside the track, that means between A and B somewhere. Let's look at it through a diagram. We have the pole, we have position A, position B. We draw the meridians of both the positions. We join them with the arc of a great circle, so we have a PAB triangle. We solve it. We have already learned in volume 1 of this series on great circle how to solve for angle A and B. And if angle A and B are found to be both acute, the vertex shall lie somewhere between A and B. So we can take any point along this where we feel appropriate, represent that by V as the vertex. We draw the meridian of this vertex from P, and we have already seen in the features of the great circle that this meridian shall cut the great circle at 90 degrees at the vertex. So this angle is 90. However, on solving for angles A and B of the PAB triangle, if we find that any one angle happens to be acute and the other one obtuse, then the vertex shall lie outside the track and it shall lie on the side of the obtuse angle. Let's look at this through a diagram. Here is the pole, here is angle position A, position B, their meridians joined by a great circle track. PAB triangle solved for angle A and B, angle A found to be acute, but angle B found to be obtuse. Now in this case, the vertex shall not lie on the track between AB. It shall be outside the track, and the closer one shall be on this side of the great circle, that means towards the obtuse angle. So we mark a point somewhere here as vertex. So here is vertex, we draw its meridian through the pole. Needless to say, it will make an angle of 90 degrees with the great circle. Now, having identified whether the vertex lies inside the track or outside the track, what do we use it for? What is our interest in the vertex that we have discussed it for so long? Now, the importance the vertex lies is in the fact that the vertex, the meridian of the vertex, cuts the great circle at 90 degrees. So this angle at the vertex between the GC track and the meridian of the vertex is 90 degrees is a very, very important feature. Why? Because this gives us special spherical triangle which is called as right angled spherical triangle, and such triangles can be much more conveniently solved using Napier's rule. To avoid any difficulty in understanding of the topic at hand, let's quickly revise the application of Napier's rule to right angled spherical triangles. To be able to apply Napier's rule, we first draw the triangle. So here is the triangle, point A, point B, point C, all joined by their arcs of great circles. So we have a spherical triangle ABC which has come up on the screen. Then we identify the angle which is 90 degrees. Let us say angle B in our case is 90 degrees. So we get ABC as the right angled spherical triangle, which has 6 parts, 3 angles, 3 sides, with angle B being 90 degrees. Now we make the Napier's cartwheel. Now to make the Napier's cartwheel, we draw the circle. We divide into 4 parts. The upper one here is divided into 2 through an arrow. The circle is now divided into 5 parts. Here we put down the part which is 90 degrees. So angle B 90 degree comes here. Now we have 5 parts left here in the spherical triangle, and we have 5 parts in the cartwheel. They are all filled in. Now these bigger parts here have the complements of the parts, whereas the smaller ones shall have the parts coming in as it is. What does it mean? We can fill in 90 minus 90 minus 90 minus here. That means here we shall have the complement of the parts. Now from B we can start going clockwise and fill up these parts in the clockwise direction from here like this. So when we go from B to clockwise, we have side BC. Side BC comes here. Then we have angle C. Angle C comes here. Then we have side AC, which comes here. Then we have side angle A, which comes here. And lastly, we have side AB, which shows up here. And that's how this is the cartwheel, which is now completed for the right angled spherical triangle. Now, if you have learned to complete the cartwheel in a different manner, it's perfectly fine. You can continue with that practice as long as the cartwheel is correctly filled in. Having completed the cartwheel, we can apply the Napier's rule. The rules are sine of the middle part is equal to product of the tangent of the adjacent parts. So this is one of the two rules. The other one being sine of the middle part is equal to product of the cosine of the opposite parts. So this is the other one. Depending on the combination, we can choose the rule to apply, use the given two parts and calculate the third one. Of course, the parts involved have to be the ones other than the 90-degree angle. And hereafter, we can apply the Napier's rule and complete our calculations. Now we reinforce our learning through an example wherein we need to calculate the coordinates of the vertex of a great circle track between position A, 10 degrees north, 40 degrees east, and position B, 30 degrees north, 100 degrees east. Now this question for the GC distance initial and final course has already been solved in our video 1. So the PAB triangle, the formation of the PAB triangle and calculation of angle A and B has been done therein. So we'll pick up the values of A and B from there. But before that, let's make the diagram for this case. We have the pole, we have position A, we have position B, meridians of A and B connected by the GC track from A to B. We have PA has colat of A, PB has colat of B, and angle P as the D-long between A and B. Now, the relevant results of solution to this PAB triangle from video 1 are angle A 60 degrees 54.8 minutes and angle B 96 degrees 24.6 minutes. Now we need to figure out as to where does the vertex lie. Now as one angle is obtuse, the vertex lies outside the track and towards the side of the obtuse angle, so vertex shall lie somewhere on this part of the track. So we can mark a suitable point V denoting the vertex. We can draw its meridian from P the pole, and that meridian shall make an angle of 90 degrees with the GC track at the vertex. Now to solve for the coordinates of the vertex, we can take any of the right angle triangle. There are two right angle triangles formed here. One is PVB, other is PVA. So we can always see which one is easier to solve. In this case, A can be directly used if we use PVA. So for this reason, just for the sake of simplicity, we have chosen the triangle PVA. So we make a cartwheel for the right triangle PVA. We have shaded the triangle that we are talking about. So you can see we are talking about this triangle now. So, and this will be the angle P as far as PVA is concerned. So we have the cartwheel coming up divided into parts. Now 90-degree angle is V, so that comes up here. Then we have in the three bigger ones, we have the complements. So we already put 90 minus out there. And now we go clockwise from V. So from V, the first part is AV, which comes in here clockwise from here like this. The next part is angle A, so 90 minus A. The next part is side PA, 90 minus PA. Then it's angle P. So angle P obviously is this angle from meridian of A to meridian of V. And then we have lastly the side PV. So this way we complete the cartwheel for the Napier's rule for the right triangle PVA. Now in the right triangle, let us identify the parts that are known to us. We know PA and we know angle A in the PVA triangle. So we mark these two parts in the cartwheel here. So we have PA known and we have angle A known. So these two values are known to us. Now we identify what we need to calculate. Now to get the latitude of V, we need to calculate PV. So PV would be one element that needs to be calculated. To get the longitude of V, we need to calculate this angle P from meridian of A to meridian of V. So that is angle P. This part also needs to be calculated. So if you see for PV, these known parts are opposite parts. So we apply sine of the middle part is equal to product of the cosines. We put the values and we get the value of PV as 59.385 degrees, which is colat of V, and therefore latitude of V is 90 minus PV equals to 30 degrees 36.9 minutes north. Now we apply the Napier's rule for these three parts, in which this 90 minus PA is the middle part and the other two are the adjacent ones. So sine of mid part is equal to product of the tangent of the adjacent ones. We put the values that are known to us and we get the value of P as 72 degrees 39.8 minutes. In the diagram we can see this is the D long from A to B, and the diagram clearly shows that the D long is easterly from A to V. Now therefore longitude of V would be longitude of A, which is 40 degrees east, and D long is east, so we add them and we get the longitude of the vertex as 112 degrees 39.6 minutes. So the coordinates of the vertex are 30 degrees 36.9 minutes north, 112 degrees 39.6 minutes east. Having calculated the coordinates of the vertex, the same can be further applied to calculate the intermediate waypoint positions. Why do we need these intermediate waypoint positions? This is because our GC track crosses meridians at different angles. Therefore, if you want to sail precisely over a GC track, the course has to be continuously altered, which is not very practical. So along the great circle track, suitable intermediate waypoint positions are picked up, and between the waypoint positions, vessel does rhumb line sailing. So by doing so, you approximate the GC track to the extent possible, and at the same time meeting the requirement of the vessel to be sailing along stretches of rhumb line. Another application of the vertex could be in composite sailing, which shall be covered in the next video. Now, when it comes to calculating or obtaining the intermediate waypoint positions, there can be two ways of approaching it depending on the suitability of the track. One is we decide on the latitude on which we would like to have the waypoint and where this parallel of latitude would cut the GC track. For that point, we need to calculate the longitude. Other way could be we decide on the longitude. So wherever the meridian of that longitude cuts the GC track, we calculate the latitude of that point. This can be conveniently done by factoring in vertex, because it shall result into right angled spherical triangle and Napier's rule can be applied. Now, in the first scenario, wherein we may have decided on the latitude of the intermediate waypoint, we can just draw the parallel of latitude that we have decided upon. Wherever this parallel of latitude crosses our BC track, this is the waypoint that we are interested in. Let's mark it with X. So the latitude of X is already known to us. We need to find its longitude. We draw the meridian of X and we get a right angled triangle PVX, in which from the latitude of the vertex we know PV, from the latitude of X we know PX. So the elements that are known to us are PX and PV. If we can calculate angle P, which will be the D long between V and X, then that shall help us in getting the longitude of X. In the second scenario, we could have the longitude of the waypoint pre-decided. So what we can do is we can draw the meridian of the waypoint, and wherever the meridian of the waypoint crosses the GC track, which is this point, this becomes our waypoint and we can mark it with X. Now, because the longitude of V and longitude of X is known, we can calculate this D long P here. PV is also known to us by virtue of knowing the latitude of vertex. So we know the PV part of the right angle triangle, we know angle P of the triangle. We can solve it for PX, which will be colat of X, from wherein the latitude of X can be obtained. So here parts known are PV and P. To be calculated is Px. Now, to help you test your understanding of the subject covered in video 1 and video 2, that means until now, we have included some questions. You can take the screenshot of the questions, they are with answers. Another 3 are here. So these 6 questions may be practiced. You can check your answers, and if you feel that there is a need, you may watch the videos again. Hope these 2 videos will help you in understanding the subject and the topic better. Thank you for watching Marine Gurukul video series. If you need any further support or if you have any feedback, please feel free to reach us on marinegurukul@gmail.com. We request you to pass on this video to all your friends who may need to know the topic, and also request you to subscribe to the channel. Thank you very much for watching Marine Gurukul video series. Thank you once again.